And so we're nearing the end of chapter 13. And so the last several lectures I've been covering lots and lots of examples across all three coordinate systems. So you should be familiar with sum of forces is equal to ma in all three coordinate systems. But this actually means I have to circle back a little bit in terms of your textbook. So there's one section that I wanted to leave to the end. We're going to circle back to section 13.3 in your textbook. And the title of the section is called Equations of Motion for a System of Particles. So we're going to do one example today on system of particles. I'll explain to you the reasoning behind it. And then we're going to move on to chapter 14 and try to cover as much of the concepts as possible in chapter 14. Okay? And so the idea is very simple. It's that obviously there are lots of objects that we've been treating like a particle so far, like a car rolling down or skidding down an incline. We consider the car to be just a particle. But obviously the car is made up of many smaller parts and components. So when you do a free body diagram or a force analysis, do you consider the whole body or do you consider each part? And when is it important to do so? So I want to first make one simple argument that even in the case of treating a car like a system of particles and you're ignoring all the little parts, it makes a lot of sense as long as you're looking at what is called the center of mass. So if you look at the center of mass of the particle or the object, then you're good. Okay, so here's a diagram. And the way that I've drawn this is you're in xy coordinates. Z is the axis pointing outward. That's your third dimension. I've got an object here indicated arbitrarily by this outline. It's like a blob. And then I have individual points. And all these points you could think of as the individual components of the system. Okay? Or you can think of them as the molecules of a body. Doesn't really matter. But they're individual points within the system. Right? And so the way you do this is you define all of the forces and the position vectors for any given point in the body. And that's given by this tiny little letter I, the dummy variable. So I'm going to state that there's a dummy variable which we call I. And across all elements I of the system, you apply the following logic. So we say this is a system of particles. System of particles I. Okay, and the idea is obviously if you want the total mass of the system must be equal to like the sum of all of the masses I. Okay, so summation across all possible values of I. Summation across all I's. Okay? So the next thing I'm going to do is once you've established that every single one of these particles has a little bit of mass mi, the sum of all of them gives you the total mass of the system m. So this is whole system. Okay? Then what I'm going to do is I'm going to actually multiply each mass by its position vector Ri. Okay? And what this does is it gives a little bit more weighting to masses that are far away compared to masses that are close. But this is essentially going to give us a weighted average, and it will help us determine where the center of mass is. Okay? Okay, so the idea is this. We can actually define something called the center of mass of the entire system by the letter RG. Okay, and the sub capital G will remind you that this is the center of mass, and we'll be using that for the rest of the course. Okay, and the way that this is defined is you take the sum across all components I of the little mass I multiplied by its own individual Ri vector, and you make this equal to the sum of the whole system multiplied by some point RG in the body. Okay? And then so you can rearrange this and you'll actually end up with this. RG can be easily found MIRI divided by M. Okay? So how many people have seen this or something related to this? Yeah, something in your calculus class, even if it's not mass weighted, you will have seen this in some form in terms of determining like a center of gravity, right? Center of gravity or some center or a centroid of an object like a semicircle. You'll be doing something along these lines, right? Okay, so now I'm going to do the force balance. So let's take a look at the force balance or the forces acting on a given particle. So on any particle I, looking at that diagram, I've actually divided it into a capital Fi and a little fi. Okay, so we can write this. So for any particle I, we have that the sum of all the forces must be equal to a capital Fi plus a little fi equal to MIAI. Okay? And so what does capital Fi and little fi mean? Capital Fi is defined as the external resultant force, meaning all of the external forces that act on a given component, right, including gravity, including any normal force from a surface outside of the whole body, those are external forces, and all of those get lumped into my capital Fi. My little fi is actually all my internal forces. So internal forces, and it's actually my internal resultant force. Okay? Okay, so that means when it says internal force, it means like, for instance, if a collar is sliding along a rod, okay, the collar is its own free body and the rod is its own free body. But if we treat the two of them as a system, a normal force from the collar to the rod is going to be equal to opposite the normal force of the rod on the collar. Those are equal and opposite reaction forces. So if we treat both of those things in total as the system, those internal forces actually eventually cancel out because they're internal to the system. Okay? And so what this means is that if you sum across all particles I, okay, here's what you would get. You would get a sum across all I of all of the external forces. You would get a sum across all particles I of all of the internal forces. And it would be summed across all I for all of the MIAIs. Okay? So every little particle within the system has its own MA, and you just add all of the MAs together in the system, and this is now mathematically true on left and right hand side. Now what happens is this is all internal forces, so this becomes equal to 0. All internal forces cancel. Okay. This just becomes all of the external forces to the system. Okay. And I'm going to show you one little neat trick. Let's look at what this MIAI is. Okay. So what I'm going to do is I'm going to take this equation and I'm going to take the derivative twice. Okay. So I'm going to take derivative twice. And what you're going to see is this. Sum of all the MI, RI single dot, vector single dot, is equal to MRG single dot. That's the velocity version. And then I'll take the derivative again. MI, RI double dot, right? And this is all true because m's are all constant in this particular case. So m rg double dot. And what does r double dot mean? R single dot is velocity, r double dot is acceleration. So this is actually an MI AI. And this is actually equivalent to the mass of the whole system multiplied by AG, the acceleration of the center of mass. So bottom line is this equation. After that little trick, I actually get the sum of forces, all of the external ones only, is equal to mass of the whole system multiplied by the acceleration of the center of mass. So what this means is everything that we've been doing, when we look at just the car and we analyze its acceleration and we ignore all the components of the system, we're really saying that the acceleration that we're solving for applies to the acceleration at the center of mass of the car. Okay? So apply for system at center of mass at point G. Okay? Does that make sense? Okay, so now this has lots of utility when you're analyzing a little bit more complicated problems. And so the first one that I want to give you an example for is, instead of thinking of a car with 1,000 components, which is complicated, let's do a simple problem that is more like the stuff you'll see in your assignments and textbook. We're going to do a system of two particles. And the two particles are going to move together. And we're going to see whether or not it's better to analyze it as a whole system or as individual components within the system of two particles. Okay? So let's take a look at what all this means. Okay, so here's my example. I'm going to have to do a little bit of visualizing here, but let's do it like this. Got a solid L bracket sitting on top of a solid table. That. Okay, and on this L bracket, I have a pulley. Okay, and there is a string that loops around the pulley. And there is a mass sitting on the L block. Okay, I'm going to call this mass B, and I'm going to call this L bracket A. And this string, I'm going to pull with force P. Okay, so you're pulling the rope. We're going to figure out what force to pull it at. The B is sitting on top of the L bracket A, and I haven't told you anything about the frictions yet. Okay, let's do Y positive upwards and X positive to the right. So we've established our coordinate system, and we have our drawing. So now let's do this. We'll say A plus B is a system of two blocks, and we'll say that there's friction on various surfaces, but we'll tell you what the mass is. So mass A is going to be 10 kilograms. And the mass of B, say it's 6 kilograms. So, table surface. Table surface, we're going to actually say that it's frictionless. So this means mu s is equal to mu k is equal to 0. Same thing. So we're applying no friction there. But we will say that there is friction between A and B. And we'll say mu s is 0.3. Mu k is a little bit less, it's 0.25. Okay, so here's what's going to happen. Imagine you pulling on the string where the pulley is. Okay, now there's no friction between the entire assembly, the entire system, and the table. So you can expect that when you're pulling it, the whole object is going to want to slide. It'll be as if it's on ice. But one of the tricky spots is the friction that's between B and A. Depending on what force you pull on the string, B could slide with respect to A, or there could be no motion. It could be static friction and there's no motion between A and B, right? So here's our questions. I'll lay them out here. So the first question, Q1, is what force, what P, pulling force, let me rephrase that. What maximum P is allowed such that B does not slide on A? Okay? So I am assuming that if you pull hard enough with P, that B will eventually slide on A, and I want just the maximum force so that they're sliding along the table, but B and A don't slide. So that's the first question. And then Q2 is find the corresponding acceleration of the system. Okay? So that's the idea. All right? Any questions on the way the problem is set up? No? All right, so first question, where do you think we should start? Do you think we should treat this as a single system with just one body and analyze it that way? Or do you think we should treat this as two separate components of a system in order to get at the answer? How many think treat as whole system? How many think treat as two separate bodies? All right. Why do you think you should treat as two separate bodies? Any idea? It's a good thought, yeah.
If you get two different bodies, you can have different, so you can have two different diagrams, of course, the FPDs.
Yeah.
So it'll be easier to analyze then.
Yeah. Okay. So the answer. So the student came up with the answer. If you have two separate free body diagrams, it's like you got two separate systems of equations to work with, and you have a lot more equations to solve a lot more variables. It's a good answer. The other thing is it's actually embedded in the question a little bit in Q1. When you think about it, it's asking for specifically when B and A don't move against each other. So B and A moving against each other, that's an internal force, right? So if you treated the whole thing as a system, you'd be hiding the internal forces and you wouldn't be able to figure that part out. So you're absolutely right. The answer is treat as two components. And I'll say that the main reason is to reveal friction force between A and B. Okay? Great. So let's go ahead and do the analysis. So you've got two free body diagrams now. So this A is actually my answer. So let's do free body diagram for, let's do it for block B first. So here's my block. So on the block, you've got a string for the pulley. Looks like the string is going to be entirely in tension, and the tension is going to be the same as the pulling force P. So it should be one of the P's. Should have an MBG downward, and I'm going to call the normal force here NB, capital NB for normal force. Okay, now, if we're to satisfy the requirement in question A that B doesn't move with respect to A, we must have what type of friction? Static friction. And what direction should the static friction be if B can't move with respect to A when you're pulling it? It should be this way, right? Okay, so this is your static friction. That's your first free body diagram. Now let's do the free body diagram for A. For A, it should be like this. Okay, and so first things first, we've got MAG. We've got normal force of the table on L. That's kind of blocking my diagram. Let me do this. NA. And then, so there's a pulley on it, right? The pulley on it. So what kind of force do you think the pulley is applying on the block? It's actually like this. The pulley is attached to the bracket. There's actually a P force from this side. But because the P wraps around the whole pulley, there's an equal P right under the pulley too. There's two P's. Okay? Then we know that there's no friction between the table and the L, and that looks to me like that's everything. Is that correct? No, I see someone shaking their head. What am I missing? Sorry? Forces from B, exactly, yeah. So I alluded to the fact that we had two components and there were internal forces. So these internal forces, if I include forces acting from A onto B, I have to include forces of B acting back on A. And so the idea is there's actually a force of the block B sitting on top of mass A. And so this NB here, the normal force, is actually acting from the L bracket on this block. It actually means that this is an equal and opposite NB sitting on top of the L bracket. And the friction force that you see here that's acting this way, it means that if there were any static friction of the top block trying to not move against A, there has to be an equal and opposite friction force here, like that. Okay? All makes sense? Okay, so if all that makes sense, then our next clue is this. We are looking in question 1 for max P. So for max P without sliding between A and B, use max static friction. Okay. In other words, that's the whole point of saying max P, is because you can have any P less than max P, but max P will give you or you'll use max static friction to get to max P. So the idea is you want force of friction to not be just the less than or equal to, but be exactly equal to mu s multiplied by the normal force of B on A and B. Okay, so as long as we apply that, we're good. So now we can do our equations. So here's our block A equation. Our block A equation looks like this. Sum of forces in the x is mass of block A multiplied by acceleration of A in the x. And looks to me like this will be 2p minus ff. B in the x direction must be mb abx. And so that looks to me very simply to be ff minus a single p. Okay, these are your mu s and b. NB is certainly unknown right now, but you can figure that out maybe. But we actually need one more equation. We've got 3 unknowns, and we need one equation. What is that equation? It's actually related to dependent motion and the kinematics of both of these objects. If B doesn't slide with A, then it makes a lot of sense. Kinematics will prove to you that if they don't move, A of x must be equal to A B of x. Okay, everyone agree with that? They have to be moving together if A is not sliding with B. Okay, so here's what we're going to do. We're going to actually do a little bit of summing of the equations. So what's the easiest way here? I'm actually going to try to eliminate P. Okay, so what I'm going to do is if I'm going to eliminate P, I'm actually going to add A and B together by making sure that I multiply 2 times of B so that I have a minus 2P, and when I add them together, it'll disappear. So here's my MA AAX plus MB ABX, 2 of these, is equal to 2P minus FF plus 2FF minus 2P, and these will cancel. And this leaves me with this. AAX is equal to ABX is equal to a single FF mu S and B MA plus 2MB. That. And then it looks like I need MB. NB, what is NB equal to? NB must be like this. Sum of forces in the Y for M A B Y must be equal to 0 because the object is not moving in the y direction. So NB is equal to MBG. And so finally we have this. We have AAX mu S is 0.3. NB is mbg, that's 6 times 9.81 divided by 10 kilograms plus 2 times 6. .81 meters per second squared to the right. And then now I just plug it back into one of my original equations. And I'll leave that to you. But then you end up solving P is equal to 12.9 newtons. OK, so that's the solution. I ended up solving both the acceleration and the force sort of at the same time because of the system of equations. It's totally fine. Okay, so does that make sense to everyone? System of particles could be as complicated as many, many components, or could be as simple as just two objects in a system where you decide whether or not to reveal the internal forces. Right? I added this little bit here, the y equation, right, for B. And you should even do a quick little double check to make sure everything else makes sense. Why don't we do y for A? So y direction for A would be sum of the forces in the y equal to MA AAY is equal to 0 because nothing moves. And then if I look at that A diagram, what does it look like? It looks like NA minus NB minus MAG is equal to 0. Okay. But NB is obtained from this one. So NA must be equal to, moving both of these over to that side, MAG plus MBG. And that makes a lot of sense because the normal force is then just the force of the surface acting opposite the weight of both of the objects, right? So everything works out and everything balances, right? Question? What's that? Yeah, I listed them as 10 kilograms and 6 kilograms, right? Everyone got the masses? Yeah.
Why is it wrong if you look at the whole free body diagram and say you're pushing with force P and then the whole mass is 16 kilograms, so you divide the force by 16 instead of 22?
Okay, excellent. So we're back to the motivation behind this section. The student is asking, why can't we just analyze the problem as a 16 kilogram mass, right? So we just went through that. The issue is you'll never be able to apply the very important point that FF is the internal friction force where you're using the equation mu s and b. And that was critical to the problem, right? It was critical to the problem because it's saying find me maximum P where that friction force hits a maximum and the whole object is still accelerating, right? So if you did that, here's what would happen. You would have a total mass. So I'll even draw it for you. It'll look like this, right? So here's my entire free body, right? So here's what it would look like. MA plus MBG downward. You'll have a single P to the right. You'll have no friction on the bottom. Those are internal. And then you'll have an NA. Sort of NA plus B, right? A plus B is sub. So this matches that in order for the block to not move. And then all you have left is a P force. So sum of forces in the X is MAX is equal to P. Now you can't solve the problem. Right? Okay, so hopefully that was helpful to you, but you got to look at exactly what the question is asking for. In this case, revealing those internal forces were absolutely critical. Okay, so yeah, one more question.
Does the acceleration and deceleration have to be
Okay, so the question is, does the A acceleration and B acceleration have to be the same in order for us to solve this problem? The answer is, in this particular case, yes, it has to be the same because we established that the two blocks have to be moving together with no sliding between them, right? So what happens if the question was a little bit more complicated and there was sliding between them? Then, at this step right here, where I established that the two were equal acceleration, you have to somehow find their relative acceleration, right? You have to somehow tell me what AB with respect to A is, and that it's equal to AB minus AA. So that's your equation, but that complicates things, right? Okay, yeah. Yeah. If the whole thing is accelerating to the right, then what, sorry? Then the friction force is greater than P. No, because the friction force here and the friction force there are internal forces. And P is the only total external force that created the acceleration to the right. Okay? All right. Let's do new chapter. Okay, so we are moving on to chapter 14. This is work and energy. Okay, so we're really just trying to introduce more methods for you. So treat this as another useful tool for solving problems. Okay? In other words, by the end of this section, by the end of this chapter, you should be thinking of problems as, oh, I might be able to solve this with F is equal to ma. I might also be able to solve it with work and energy. I should be able to get to the same answer. These are just tools in my toolbox. Some problems are more amenable to work and energy solutions than they are to F is equal to ma solutions. So that's what we're going to teach you, to look for clues as to which is the better method. Okay? But don't think of it as, oh, this has to be, this is, I'm going to categorize this as a work and energy problem only. Okay? It shouldn't be thought of that way. So we're going to define what these terms are. So let me first give you a definition for work. So this is going to be what we consider to be work done by a force. So work done by a force on a particle. Okay, so here's the definition of work. I've got a path that the particle is moving on. Particle starts there, ends up over here. It's moving this way. Okay? So everywhere along the path there's forces acting on it. So let's just say there's a force acting on this particular particle like that. And that force is applied while the particle is moving and while the particle makes a little bit of a displacement. So I'm going to show you a tiny little displacement vector right there. So this vector represents a tiny little bit of my path. Okay? dr, this is a infinitesimal displacement along the path. Okay? and we have an angle between the force and dr. Okay? And so the definition for work done by a force on a particle moving over small displacement dr is this, given by a capital letter U. Okay, in this case, it's a little du equal to F dot product dr. Okay, so I'll start with that right there. So what does this mean? It means that du is my change in work. Okay. Okay, so let me write this out again. It's equal to F dot dr. Okay, so the first things first, when you do a dot product of two vectors, what does it mean mathematically? It actually means that one of the vectors ends up being a projection on top of the other vector. You should have learned this at some point, right? And so what this means is when you do a dot product, you can easily convert this into something that looks like this. F times cosine of theta multiplied by the dr. So the dot product goes away and I just take the cosine of theta. Okay, so it means that only the component of F acting along the path does work. Okay? So only component of F along dr does any work. Okay? And then so when you do work along path from the start to the end, so let's say from point 1 to point 2, what do? What you do is you do an integral. So this would be work from 1 to 2 is equal to you marching along the entire length of the path from position 1 to position 2, and then adding all of these together. So it would be F cosine theta dr. Okay, and really this should be like this. Let me just redo that first for a quick second here. So let me just do this. From 1 to 2 of all the du's. This is equal to as if I integrated from position vector r1 to r2, where I did F dot my drs. But then if I do all of my projections, and I do just F cosine theta, if I'm marching along the path, every little bit of dr vector, as long as I've already taken into account cosine theta is the angle between the force and the displacement, then I'm just using ds as my tangential component. And I can just go S1 to S2. Okay? So that is essentially what work means. And what does the integral mean? Obviously, integral is area under the curve. So So integration is just area under the curve. So it's kind of like this. As the particle is marching along the path, you go starting from S1 and you're moving all the way to S2. The path is kind of winding. But as long as you keep multiplying it by f cosine theta, okay, then what you're doing is f cosine theta times every little bit of ds, just finding the area under the curve like that. And this is your work by force F along path. From S1 to S2. Okay, a couple other notes. So if this is, let's move this up here. Okay, so notes. The first one is anytime you have two vectors and you've done a dot product, it always becomes a scalar. So work is a scalar quantity. So we can write this as this, du equal to f dot dr. Scalar equal to vector dot product vector, right? Okay, so it's a scalar, which is great because it means you don't have to worry about directions in problems that relate work and energy. The second thing is let's note what the units are. So the units of work must be like this. So du is equal to an f dot dr. So this is a Newton, and this is a meter. And so we call this joules. Okay, so another way of writing this would be kilogram meter per second squared times meter. So this is kilogram meter squared per second squared, but we actually just call this a joule. Okay, and hint, hint. Obviously, this is the same unit as energy, which we will get to in a subsequent class. Okay. And a couple more notes. Whoop. So just two more things. First thing is remember moment or torque is also in the units of Newton times meter, right? But clearly when you do torque and there's Newton times meter, just remember that we're going to deal with this in a subsequent lecture, but the moment is obviously equal to not the dot product, but something like a cross product, right? So say you have a beam on a pin and you apply force. Is everything okay? Everyone seems a little bit agitated, right? Okay, but I just want to bring to your attention, right? Obviously, this is still force and a distance, right? But we're not talking about work in this case because this is not a scalar. When you do a cross product of two vectors, you still end up with a vector. You got to make sure you have the directions right because it's a right-hand rule. So in this case, R goes this way, force goes this way. You curl your fingers, your thumb goes out. So the moment actually has a vector along the axis of rotation, right? So this is moment. Don't get confused. Same units, but not the same as joules, right? And then one final point, 4, is be very, very careful of signs. So signs, okay? If you see positive work, it's an indication that the force is clearly in the same direction as the displacement, right? Force and displacement, same direction. Okay, so it means when you say, oh, this force is acting on this particle and is work on the particle, like gravity. Gravity is positive work on the particle, but only when the particle is moving down because gravity is pulling it down. And if it's negative work, because of the way the cosine theta angle happens to be oriented, force and displacement are in opposite directions, right? Okay, so what does this mean? What this means is you're going to do a free body diagram. Okay, so I'll give you an example.
503.
What's that?
503.
Sorry. You guys have to run? Yes? All right. 2 seconds here. So here and here. So let's say the block is moving up an incline. This force that's moving in the same direction as it moving up the incline gives you positive work. This one that's going against in the opposite direction is negative work. Okay? All right. My apologies. Got too excited there, but I'll pick this up again on Monday. Actually, so one quick note. Next week I won't be here. I won't be on campus. So Monday and Tuesday, there'll be a substitute instructor, Professor Lee Dan Yu, will be doing the lectures. I'll be back on Thursday. All right?